Great. So the last talk in this session is a different perspective on all this correctness and incorrectness stuff, comparing these logics based on Kleene algebra. And our speaker is Lena. We'll just give 1 second for the microphone.
Let's go.
All right, great.
Okay.
Take it away.
Thanks for the introduction. I'll present some stuff that Benjamin Kaminski and I have been working on. So we have already talked about several program logics today. Whole logic, incorrectness logic, of course, but there are many, many more, such as sufficient incorrectness logic in the talk of this morning. And the objective of this talk now is to build a taxonomy of program logics from the perspective of predicate transformers and Kleene algebra with top-end tests. So yeah, we will try to build a picture such that we can fit all of these logics in. And yeah, let's start with discussing some program logics. Consider this very simple depiction of a program here with a set of final states highlighted, and then the weakest precondition is just the set of states from which computation always terminates, and always terminates in the states satisfying the postcondition, so these orange states here. And we then say that a triple, oh yeah, so these are in this example states 1, 2, and 3. And we say that a triple is valid for total correctness if all of the states in the precondition are contained in the weakest pre of the postcondition. Now this weakest precondition calculus was introduced by Dijkstra, and there are many variants of this today. But one variant that was already introduced by Dijkstra is the weakest liberal precondition transformer. And this includes the states from which computation diverges. So for this example, this is state 5, which is then also included in the weakest liberal pre. And we then say that a triple is valid for partial correctness if all of the states in the precondition are contained in the weakest liberal pre. Yeah, so now we want to reason about non-deterministic programs. So here you can see that from state 4 we can either terminate in state 3 or 4. And as a consequence, we have to choose how to deal with non-determinism. And there are two main methods. One is we resolve non-determinism in our favor. This is called angelic. And we can also, if we don't resolve in our favor, it's called demonic. And this behavior can be included in the transformers, giving us two variants of each. So we now have four different transformers to look at. And what exactly is the difference between them? Well, the demonic weakest pre transformer requires all possible paths of the execution to terminate in the postcondition. So for this example, these are still states 1, 2, and 3. But the angelic weakest pre transformer says, okay, it's sufficient if there exists a path to the postcondition. So here you can see there is a path from state 4 to the postcondition. So state 4 is actually now included. And then the angelic weakest liberal pre additionally includes the states from which computation diverges. So here's state 5 again. Or in this example, actually, all initial states are included in the angelic weakest liberal pre. And the demonic weakest liberal pre again removes state 4 from the precondition. So yeah, you can also see that there is an order between these sets. So the demonic weakest pre is the smallest set, and the angelic weakest liberal pre is the largest one. Now, to keep things a bit more simple, we will for now focus on these two variants. So we will assume that the weakest precondition or non-determinism in the weakest precondition transformer is resolved angelically, and in the weakest liberal pre it's resolved demonically. And this gives us now two triples, one for total correctness, and now this is actually, since we're using the angelic variant here and not the demonic, this is actually equivalent to what was earlier called Lisbon logic or sufficient incorrectness logic. And yeah, we also have a triple for partial correctness, but here we're using the demonic resolution, which is the standard choice. Okay, so we're going to complete this picture in some sense, and for this we can first add two contrapositives of these triples here. So B is included in the angelic VP of C, WP, sorry, exactly if and only if the demonic weakest liberal pre of C is included, of the negation of C is included in the negation of B. Okay, so weakest pre and weakest liberal pre are both backwards transformers in the sense that we start with a set of final states and compute a set of initial states. But this can be also done the other way around. If we start with a set of initial states, here 1, 2, and 3, we can compute the strongest post condition, which contains the set of states reachable from these initial states. So in this example, these are states 1 and 2. And we then say that a triple is valid for incorrectness if the post condition is included in the strongest post of the precondition. And there's actually also a liberal variant of this calculus. And now recall that the difference between WP and WLP was the states from which computation diverges. And now dually, for the strongest post perspective, the liberal calculus includes those final states that are unreachable. So in this case, state 5 is included in this set of strongest liberal post. And we then say that a triple is valid for partial incorrectness if the post condition is included in the demonic or in the strongest liberal post. And this is actually equivalent to what Cousot called necessary preconditions. Yeah, so a lot of renaming here. I'm sorry about that, but we'll resolve that. And we also have to decide what to do with non-determinism here. And as for WP, for now we will focus on the angelic variant of strongest post and the demonic variant of strongest liberal post. And these are this is like the standard choice of incorrectness, so the incorrectness logic that you're familiar with probably. Okay, so let's add these triples to our picture. So we now have here partial incorrectness and incorrectness, and these both also have a contrapositive. And now, interestingly, there's another connection here, namely a Galois connection between here, the partial correctness, and the contrapositive of partial incorrectness. So this leaves us with three blocks kind of here, the correctness, then the partial correctness and partial incorrectness, and incorrectness at the bottom. Now this is a very nice symmetric looking picture. So let's look at this from another perspective and see if we can kind of confirm these results. And well, the perspective we're going to choose is actually Kleene algebra with top and tests. Now, Kleene algebra was originally developed as an equational characterization of regular expressions, and then extended to Kleene algebra with tests by Cozen to reason about programs, and then further extended to Kleene algebra with top and tests by Zhang, de Amorim, and Gaboadi to actually for the purpose of reasoning about incorrectness. So this fits very nicely in here. Okay, I'm going to skip formal details and just give an intuition of how we can use Kleene algebraic equations to specify program properties. Yeah, so in general, a program in the Kleene algebra is seen as a program is modeled as an element of an algebra, and we'll focus on relational algebra, where we can think of a program as a relation over program states, and an initial state is related to a final state if there exists an execution from one to the other. So yeah, and we can compose programs, and in the relational setting, this is simply composition of relations or programs. So here's the program that we've seen before, and if we want to compose to this another program Q, which is just skip, so does nothing, so this is the identity relation, then we can compose this, and we get a new relation which contains exactly these highlighted pairs of states. Yeah, and tests are special elements of the algebra in that they are subsets of the identity relation, and they can be negated. So the relational representation of a property fulfilled by states 1, 2, and 3 is exactly this here, and we can also compose a test to an expression which then gives us this new relation. So we can see that effectively composing a test removes those states that fail to satisfy the property. And we can, of course, do the same for a property on finite states, which gives us this relation. So this is actually only containing the pairs 2 and 2 and 3, 2, as these are, so to speak, the only paths through this picture. Now for incorrectness, for example, we are interested in comparing only the finite states of such expressions. And this is not possible in Kleene algebra with tests, but what can we do? We can add a top element, which in the relational setting is just the universal relation, relating everything with everything. And if we compose this top element to the relation we had before, what we get is a new relation where all initial states are related to the final states of the previous relation. So, the point is that these all initial states are somewhat constant. So we can now compare the codomain of relations and also the domain. Okay, so let's see how we can actually express program properties. We can express partial correctness using this equation here, stating that a top BPC is equal to top BP, and this left-hand side of the equation selects all finite states that are in C and can be reached from B. You can, you can see this in this picture here as well. The right-hand side here selects all finite states that can be reached from B. So if these two relations are the same, then actually all executions that are started in B have to terminate in a state satisfying C, which is partial correctness. Okay, and we can give a very similar equation for incorrectness. Namely, here we compare again. This is the same. We can compare all finite states that are in C and are reachable from B to now all finite states that satisfy C. And if these two relations are the same, then for all states in C, there must exist a state in B from which C can be reached, which is exactly incorrectness. Okay, so what about the other properties that we've seen? It is kind of folklore knowledge that it's not possible to express demonic or the standard total correctness in Kleene algebra. But we found out that it's actually possible to express this angelic or Lisbon total correctness. This is something that we found out. And the equation for that is actually very similar to what we've seen before. Now we compare here all initial states that satisfy B and can terminate in C with all initial states satisfying B. So if these two relations are the same, then all states in B must have some execution to a state satisfying C, which was exactly this Lisbon or angelic total correctness. So let's summarize this. So we have seen that we can give cut equations or top cut equations for partial correctness and incorrectness. And now partial incorrectness, as we've seen before, is just the contrapositive to partial correctness. So we can also give an equation for that. And we have also seen that we can express Lisbon total correctness. Now you can see that all of these equations look syntactically somehow similar. And we wondered, there must be more equations fitting this pattern, right? And in fact, there are. For example, this one here and this one. And now the question is, what does this mean? What kind of properties are expressed by these two equations? And now, interestingly, the bottom one is an equation for angelic partial correctness. So this is one of the variants that we skipped before. but the top one is not angelic partial correctness, which might be like, yeah, what you would expect. So this is kind of weird, and everything up until now was very symmetric, and now, yeah, this is somehow asymmetric, and the reason seems to be this different resolution of non-determinism. So let's extend the picture that we've seen before to accommodate these different resolutions of non-determinism. Yeah, so this is the picture we have seen before, and I'm just going to remove the names and make some space for the other triples. And well, first I'm going to add what we've seen before, which are these demonic weakest pre and angelic weakest liberal pre transformers. And we've also seen before that there's an order between them. So the demonic weakest pre is the strictest transformer, so to speak, and then angelic WLP is the most lenient one. So we get an order of implication, which I add here to add more arrows to this picture. And we can do the same in this upper right part. And now if you look at this, you would kind of expect something similar to exist here, right? Something dual for this bottom half. And so this doesn't exist in literature, but we were actually able to define a demonic strongest post and an angelic strongest liberal post transformer that fit into this picture, and that they, in particular, also fulfill these implications. And then, well, these added triples also have contrapositive relations, which is nice, the top half and also the bottom half. So this is now what we have, and I won't add anything more. But yeah, this is a lot. I mean, but that was kind of the point, to have like an overview and maybe a structure, see what structures are there and how we can relate them. But yeah, so let's look at the properties that we can express in top cut, because I've mentioned that there is some kind of asymmetry. And well, you can see there's a gap here. And yeah, these two can be expressed, but these can't. And yeah, the question is why, and we think we have an answer to that, which is just that we can analyze a program forwards and backwards, but it will always run forwards. So in some sense, it makes sense that there is a difference between this top backward analyzing side and the bottom half here. But yeah, there's another thing that is interesting, which is supposedly incorrectness and correctness are two sides of the same coin, right? So incorrectness is here. So we would expect the other side of the coin to be here, no? But total correctness is actually here. So yeah, what is this? And well, we can partly answer this. Here is actually these Lisbon triple or Lisbon total correctness that we were showing earlier. And well, this I don't really know what this is, but we're working on that. So the takeaway message is kind of, this picture is not as symmetric as it may look on the first glance. And yeah, we're working on figuring out where these asymmetries are coming from and how we can give like an intuitive explanation of how they relate. And we're also looking at like the effects of different assumptions on the program on this picture. So I think this was mentioned earlier as well. If the program, for example, always terminates, then the picture kind of collapses in some dimensions. And similarly, if we have a reversible program, for example, the dual thing happens for the bottom half. And another thing that I think is interesting, all of the triples I mentioned here assume something either for all initial states or for all final states. But I think especially for reasoning about, or for proving the existence of a bug, it would also be interesting to have a logic that expresses something like there exists a single path from a state satisfying the precondition to a state satisfying the postcondition. Yeah, that's all I wanted to say. Thank you.
Okay. Yeah.
I mean, that's a fascinating talk. You know a lot that I wish I knew. This bit on existential triples is very interesting. I mean, I played with around with those, and I mean, if I understand what they are, the difficulty I saw is they don't play well with sequential composition.
Yeah, yeah.
Right? And then I don't know what to do about that. But if you think like, what's a transition subvariant? A subset of the transition relation? I mean, it's this kind of thing you're getting at, right? In order to prove incorrectness, we don't need to cover everything in the pre or everything in the post, right? As long as we get one of these things, we're good for proving incorrectness. But I guess what puzzles me is that it's hard to see how it works with program analysis. This is no criticism, I'm just...
No, I don't have an answer to that, that's fine.
Maybe you'll answer that for us. But I mean, fascinating talk,
Yeah, it's just a thing that I think is interesting, but I don't really have a working proposal. Yeah.
Great. We have time for one more quick question.
You mentioned that there's this asymmetry between forwards and backwards analyses, and as part of your future work, I see the question when the program is reversible. But in this Kleene setting, and for non-deterministic programs in general, aren't they all sorts of trivially reversible? Like I can take the reversal of a regular set of traces and it'd still be regular. So do you know why they're asymmetric?
Well, I think the problem is that if you have non-deterministic choices, say you have a program which is non-deterministically choosing between skip, so doing nothing, or diverging. This is a setting that cannot exist in the reverse way because there cannot be a final state that is unreachable and reachable. You always have, for all final states, you always have either unreachability, so no initial state can reach that state, or there are several ones or whatever. But in the other way around from an initial state, it can be that you either have or that you have non-determinism, non-termination, and termination. So I think this is like the main point why these Kleene algebra equations are not completely, or in fact, let me show you. This equation here is something like angelic partial correctness, but it says something like from all initial states, computation either always diverges or reaches, or there is a path to the postcondition, which is not exactly angelic partial correctness because, but I think that's the reason. But
Thanks.
Okay, great. Let's thank the speaker again.